speak. And a real pleasure to have kind of all of the background material for my talk. But before I start, I think we should thank the organizers for putting together such a nice conference. Yeah, I guess I'll just a little bit of motivation. I mean, Piotr did a very good job explaining sort of background, but let me just remind you that if we look at mu-based synthetic spectra, then we get a deformation. And I'm going to try to stick to Piotr's. I usually flip the arrows, so it's very confusing to me that it's this way around. But where we, on one side, get something like the derived category of the moduli stack of oriented formal group, formal groups. And on the other side, we get spectra. And while Piotr's definition is extremely useful for actually doing math, I kind of think of sheaves as being like a generators and relation type category, and I wanted something a little bit more geometrical, or like where this all has to do with descent, and kind of I feel like we should see this descent somewhere. And perhaps a motivating result is a result by Rod Gregoric, which says that this is actually, I'm gonna put this in quotations, but this is roughly quasi-coherent sheaves on a non-connective spectral stack, which is the moduli stack of oriented formal groups. And you might ask, is there some sort of stacky thing I can put into QCO and so that I get mu-based synthetic spectra? And this was actually also done by Rock. These are excellent papers where he kind of geometricizes or like makes formal these ideas of algebraic geometry in chromatic homotopy theory. I highly recommend reading them. But he shows that this category is roughly quasi-coherent sheaves on, well, you take this stack from over here and you just make it into a connective stack the only way you know how. And the reason why I put this in quotation marks is because really what you ought to put in here is some sort of incoherent sheaves, which on this side is a well-studied phenomena. On this side, there's perhaps some definition you can find in SAG or something, but it's not really very well studied. But on this side, it's kind of just whatever Rod defines it to be, and it works for what he's doing. So that's all well and good, but it doesn't really feel that satisfying to me because among other things, I don't really see how to do this for other stacks. So kind of the thing that motivated me is question, can I produce deformations for all, I'll say geometric stacks. The reason why I say geometric is because this is some adjective you put on your stack so that the stem spectral sequence is some like feasible thing to try to compute with. One thing perhaps also I would like, if I am able to solve this, is that it should have a few properties. So this is like an algebraic stack. It has to do with algebraic information. This is a spectral stack, purely like defined in terms of spectra. I would like this perhaps to be some sort of synthetic stack, or I call them filter stacks, but that's kind of, I'm not happy with the names, so suggestions are welcome. Is there synthetic type stacks? And follow-up thing is that, you know, one, like producing stacks is good, but I want it to somehow be compatible with geometry. So geometry. So this tells you maybe two things. It tells you that somehow you should know about the descent spectral sequence of the stack, but also it tells you that if I take something like spec R or some ring spectrum, this should be sent to modules over the Whitehead tower bar in filtered spectra, which, among other things, tells you that the only interesting spectral sequences you get are the ones you get once you start imposing geometry. Because the spectral sequence is the one that degenerates on the E2 page, and it just says that the homotopy equals the homotopy. So it's very not interesting. I'll do it this way. So if I want to somehow do synthetic stacks, maybe I should do rings and synthetic spectra as the test objects, but we all saw that this is somehow secretly happening over filtered spectra. So I'll kind of start with this. And if you want to define a stack, you better first define a topology. So first theorem I kind of get to is that, let me give you a definition first, what makes everything better. The map of, so this is now an algebra in filtered spectra. And I remind you that we put the day convolution monoidal structure on filtered spectra. This is kind of important because you want your filtrations to have the property that if you have something in filtration A and something in filtration B, the product should be in filtration A plus B. But we say that it's flat. If so, let me first write down the statement because this is something that is very well known to people. So 1 pi 0 of A to pi 0 of B. This is now this T structure that Piotr defined where things are connective. If in degree n you have something which is n connective, this should be, and this is just shorthand for the bigraded homotopy or the bigraded group, which is just pi in degree n. It's pi n of xn. So let's down. I n xn as n varies.
This is like pi 0 for some T structure.
This is pi 0 for some T structure. Yeah, and it's flat as a map of the Dirac rings. This is this notion of graded rings, where they're graded commutative, studied by Piotr and Lars. And this is kind of the natural place to do these type of things because these are the type of maps that actually show up when you try to do atom spectral sequences. But you want some other condition. You want.
You mean like it's like, because this is a map of filtrations, right? So
Yeah, but
map
when
of like filter.
no, once I take pi 0, I get a graded ring. This is the, I think.
The graded. Okay, fine. Yes.
Yeah, yeah.
Yes, very good. Yeah. Is that the same thing as like just flat in each?
No.
No.
I mean, first of all, like the nth graded piece is not necessarily a module over the nth graded, like there's no ring structure. But it's roughly, you should think of, there's a graded tensor product, and it's saying that this is exact.
Okay.
And you want something else, namely you want this condition that some people might know from algebra. You want that pi n of A tensored over pi 0 of A with pi 0 of B. This naturally maps to pi 0 of B, pi n of B. You want this to be an equivalence or an isomorphism. And this is kind of just the natural definition of flatness for a T, like you have a T structure in some category, you can ask what a map of rings should, what it should mean for a module to be flat. And this is kind of the thing Jacob writes, and it's sort of equivalent to the derived tensor product being T exact. But let me just say that there's a different thing you could ask. You could ask that these bi-graded homotopy groups seize flatness and the same type of phase change condition. And this turns out to be that this is stronger than the other one, but there's a relationship. It comes in form of a theorem, which I guess is due to Shell-Bakan. It's not really a difficult thing, but you have this the puncta, which takes a ring spectrum to its Whitehead tower. Sends pi star flat maps. So this kind of tells you that if I have some sort of understanding of the flat topology for rings, then I get an understanding of the flat topology or how the flat maps look for some folded ring spectrum, which is in the image of this Whitehead tower.
But pi star is the second one. Is that what it's called?
So pi star flat, here I just mean you have a ring spectrum, you can take its pi star. This is a graded ring.
Okay, fine, yeah.
Yeah. It turns out that this, like, once you take if you look at the homotopy groups of a full dot ring or any full dot spectrum and it's in the image of the Whitehead tower, then there's a lot of redundancy. I mean, kind of just, all the same homotopy groups moving around, which is why you can kind of push this pi star information into pi 0. For the interested, you might know that there's this notion of flatness due to Jacob Lurie, or at least very prominent in the high algebra. And in this case, you would get this stronger bi-graded flatness condition. And this is perhaps more natural if you're only interested in spectral algebraic geometry. But I won't really focus on that today because I want to say stuff about synthetic spectra. And if you study the atom spectral sequence, what happens a lot is that the map, you want something like map from E to E tensor E is flat. This you only get on homotopy groups, not on this in this Jacob sense in general. So here's a theorem. There is a binary Grothendieck topology on cumulative algebras in full dot spectra. What covers finite collections of jointly faithfully flat maps. Here, that being faithful just means that tensoring or base changing along this map is conservative. All right. So this tells us we can at least apologize to my board work. It's kind of confusing. Sports.
Whose theorem is this?
This is me.
Nice.
Yeah, I guess everything that comes from now on is me. At one point, there will be a theorem by Robert Birkeland, but maybe I'll only say it out loud. But This style allows you to give a definition. A full dot stack a sheaf of spaces on units of algebras in full dot spectra. So let me not spell out what this means, but it means roughly that we can descend along flat maps. And
how does this relate to like stacks over A1 mod GM? The difference in
stacks over A1 mod GM. There's a map from this category to stacks to stacks with a map to A1 mod GM. Yeah, essentially you can, like, every stack is a colimit of affine things, and affine things, like in this sense, turn out to be affine over A1 mod GM. So you do this in a functorial way, and then you take the colimit back up again. And then we just follow up the definition that if x, so filtered stack, then I define quasi-coherent sheaf x to be the limit over all spec R mapping to x of modules over R. Now R is a filtered ring in this case in filtered spectrum. It's kind of the standard game of how you define quasi-coherent sheaves if you have some sort of notion of algebras. And it just turns out that this is also what works in this case. Are there any questions while I raise?
In this a sheaf or hypersheaf?
I want to say sheaf, but perhaps I want to say something like accessible sheaf or something like this.
But because usually in the unfiltered setting, don't usually assume the hypersheaf function.
I don't think so. I don't think Jacob does, at least. And I mean, a lot of the start of this project is just doing what Jacob does, but yeah, like the proofs are the same. There's not a like this proof is hard, but it's what Jacob does, and it's just because computations are hard.
Yeah.
Everything else just category theory.
Just gonna also this hot theorem. What's the more general thing that I can set with?
You can take any symmetric monoidal stable infinity category with a right complete T structure. This theorem is true. If you define things like this way, it works. Yeah, I mean, in the end, and this is kind of a like the way you prove these things is you want to study some sort of Kuhn spectral sequence. And you can set it up the way Piotr did yesterday by take the Whitehead tower of M, sends it with the Whitehead tower in full dot object of N over the Whitehead tower of R. This associated spectral sequence is some sort of new thing, but if R is connective, which everything in the image of the Whitehead tower is, then this is a complete filtration, so you can check things on the associated graded, but we've set up the term, the way we define flatness exactly so that we have descent on the associated graded. Are there any other questions?
So you also prove then that this topology you have like sheafification for accessibles.
Yeah, I have a proof of this. I think there might be a gap. Either way, I have what I'm going to tell you now is that there's a good way to produce folded stacks. If we use this result by Scholl-Bakan, then we can, like, almost instantly, we can see that there are there is a full limit preserving functor stacks to call this category F stacks. I know it looks like formal stacks, but bear with me. And it satisfies the relation that if I take the associated filtered stack of something affine, then I just get the affine thing presented by the Whitehead tau of R. So I mean, this is just saying that it's induced by Lefkan extending. And this gives you a very nice collection of things. Like basically everything I care about is in the image of this functor, or some version of it. If I get to the end, or if I have time at the end, I'll talk about the even filtration and how you can think about this in this picture, which is something that isn't exactly this functor, but it's like a version of it. But I also want to say some of the kind of cool things. So here's a different thing. So you can, one of the like really useful things if you want to do algebraic geometry is you might want to have something like faithfully flat descent. And one version of this is the following theorem that this is proven by Jacob in like algebra or in DAG or something for ring spectra. So here R2S is a map of commutative algebras in filtered spectra. And I'm secretly gonna ask that they're connective as filtered spectra. This is quite important for the proof to work. If you know some of this like infinite topologies, Robert Birkeland machinery, then there's a nicer proof, but this is unpublished work, so at some point. But then you can look at modules over R in filtered spectra, and this maps to the limit over the potential category modules over S tensored with itself over R plus 1 many times. And this is you need to put all your conditions in. So if this map is faithfully flat, then we get that this is an equivalence. Yeah, this has a pretty interesting corollary, which is that if maybe I'll give it different names. If A to B is a map of ring spectra now, which is faithfully pi star flat, then you get that well, now not filtered spectra, but you just look at modules and spectra. I apologize for this being hard to read, that this is an equivalence.
Can you read out the indices?
So this says S to the power of tensor dot plus 1. And this is perhaps not too difficult to believe, because by Shaul's theorem, we get that this map is a flat map of filtered rings. It turns out it's also faithful. This is something you can also check. And then, so we definitely get this type of descent. But if you invert tau on both sides here, then you actually recover this category, because inverting tau is like tensoring with a dualizable object in filtered spectra modules in PRL. Okay. Are there any questions about this statement? And I want to point out that this is here I don't require connectivity, because once again we kind of push everything into pi0 filtered. It is kind of something that Piotr talked a lot about, and it's kind of part of this like tau philosophy, that you map everything into something where it's like artificially connective, but you can then do arguments, and sometimes math just works.
Yeah. So I get the logic right that you said. So in this theorem, you said that Jacob proved this for like ordinary rings not filtered, but
Yeah.
connective.
For connective.
You're saying when you do this filtered thing, suddenly you also get this for.
Yeah, and you actually get something else also. This is the weaker topology. I'm not asking for this Jacob style flatness. I'm asking just for unhomotopy groups, you get a faithfully flat map of Dirac rings. Yeah. So this corollary, and I guess also that theorem, was previously both proven by Robert Birkeland in much higher generality, but this is not yet available for the average person to read about it. So maybe soon. Is this readable if I have it down here, or do I? Right, but let's get back to the picture. So now I really want to study deformations, and we can prove following theorem. Oh, I'm way ahead of time. So if X is a geometric non-connective spectral stack. Here I just mean sheaves on all ring spectra, and this geometric part, it means specifically that it has a flat cover by an affine, but you should just think of it as being some like niceness condition. Then we get a diagram start with quasi-coherent sheaves on X, and we can look at quasi-coherent sheaves on the associated filtered stack. And it turns out there's a version of the synthetic analog in this picture. This is perhaps not too hard to believe. I mean, somehow I take like, this is some limit of module categories. This is some limit of modules in filtered spectra, and the Whitehead tower is lag symmetric monoidal. And you can prove in the case where it's geometric, then actually it refines to a natural transformation between these two diagrams. So you get this limit. But you can also invert tau. And it turns out that when you invert tau, you actually go back to quasi-coherent sheaves on X. And the composite is the identity. But you can also set tau to be 0, quotient by tau. And then you get something which is actually purely algebraic. So if you have a stack, you can always get an associated Dirac stack in the sense of Piotr and Lars, and you can take quasi-coherent sheaves on this, and it turns out this is what you get. Up to some sort of shearing, but at least on objects, this is true. And this is really given by taking some sort of like homotopy groups. Yeah. So this already tells us that this is perhaps quite a nice theory. And I should tell you that also this lives over filtered spectra. This is perhaps not so hard to believe. It's a limit of things living over filtered spectra, so it better self be living over filtered spectra. And if you look at the the right adjoint, which I call cohomology, this is some version of coherent cohomology. This now lands in full dot spectra, but of course, I could invert tau on both sides here, and it turns out then I just land in spectra and I get the cohomology. Yeah. So among other things, one thing you can prove is that if you try to take the coherent cohomology of something which is in the image of the synthetic analog, then you get a full dot spectrum out of it, and it's the full dot spectrum whose spectral sequence is the descent spectral sequence for this quasi-coherent sheaf. Right. So, are there any questions while I erase on the other side?
You think of like what you wrote on QCO there to be an open close decomposition of x to the tau?
I want to say yes. I mean, in the sense that it's like what Clark described, yes. But I don't have a good notion of open immersion or spectral for full dot stacks yet. And you could ask like how this interacts, but kind of it's easier to kind of access the flat topology than it is to access something like Etal or Sariski. I really just don't know how to do these things yet. And I think that's a really interesting question. Are there any other questions? Then I think because it's Friday afternoon, we should just do some examples and then maybe end early. Okay, so let's start. So if we have some E-infinity ring spectrum, which is Adams type, this is the same niceness condition that Piotr needed. I mean, among other things, it implies that R to R tensor R is flat. Then I'll define M subscript R to be the geometric realization of applying spec to the Amitzer complex. So this is something whose descent spectral sequence is the Adams spectral sequence for like the R-based Adams spectral sequence. And we want to, at least for me, I want to at least at some point come up with some stack whose full dot quasi-coherent sheaves is synthetic spectra. And this is so far my best guess. I mean, at least it has the right descent spectral sequence. So theorem, there is a Lex symmetric monoidal T-exact functor R-based synthetic spectra into QCO on MR tau. But unfortunately, this is not an equivalence in general. But it is, however, fully faithful on X on R-based synthetic spectra, which satisfies that X mapping to limit X tensor mu to the dot plus one as an equivalence. So this is essentially those spectra for which the synthetic atom spectral sequence converges. But let me just provide a warning that this failure being faithful can be quite dramatic. Yeah. To give you one example, you do something where the atom spectral sequence is very far from converging, say the rationals, or maybe very far from having good information, whatever you want to say, then you get this synthetic analog from spectra into synthetic spectra based on the rationals, and then you can apply this functor to eigenstruct to Q on and Q tau. But this turns out to be modules in full dot spectra over the rationals as a constant thing starting at degree 0. And this can never contain spectra as a full subcategory. In particular, it's C-linear. Rationally bound. Yes, this failure can be quite bad. So, are there any questions for this stuff? Let me say before I erase that if you put together this result and the existence of this functor with these properties, and the fact that these things are tensor over full dot spectra, then you can really see that doing these tau formalism arguments in either category is roughly the same, because in the end it all happens in full dot spectra.
So you're also saying this theorem that this functor is also like linear over filter spectra.
Yeah.
Is it automatic from what you wrote down there, or is it like?
Depends on how. There's two ways to define it. You can define it either by using the universal property of synthetic spectra, which says something like co-limit preserving functors out of syn R is the same as exact functors out of this SP SPFP arm. Yeah. Like this synthetic spectra is an example of a presentable stable envelope of an exact category, and the exact category is these finite, like R finite projective spectra, and the exact structure comes from saying a sequence is exact if it's exact on R homology. And if you use this thing to construct it, then you don't get any of the nice properties without trying to do something quite clever. You, on the other hand, ask, what if I just do the cent or like synthetic algebraic geometry in syn R? Then you can ask, instead of resolving the Whitehead tower, you can ask if resolving like QCO for some like the synthetic analog of R, like this type of construction of the stack in there. And it turns out that the category you get is actually equivalent to this thing. And it happens because while we don't always know that syn R is modules in full dot spectra, it turns out that once you pass to modules over the synthetic analog of the ring you're interested in, this is always equivalent to modules over the Whitehead tower of R in full dot spectra. This is also, in hindsight, the reason why I could get away with only ever thinking about rings in full dot spectra. Because for anything reasonable, and this reasonable depends on R, you never get anything that isn't just geometry in full dot spectra. Are there any other questions?
Is there any chance to describe more explicitly that functor?
Yeah. But maybe we do it afterwards. It takes a little bit of time. But if you do in words what I just said to Leonard, it works. So I guess the important part is that because synthetic spectra has a lax symmetric monoidal functor to filtered spectra, you can try to, I'll just do it now. You can descend along the unit map from arm in synthetic spectra, and you can do the same, but now for this functor is by some people called the signature. I don't know if I like it, but you can try to do the same thing in filtered spectra. But it turns out that if you take the signature of anything which is an R module, so in particular, or a new R module, in particular new R, you just get the Whitehead tower of R. And then this is just a natural transformation of the signature function. So really it is just given by descending the signature functor. But you can also give like a more explicit like construction by looking at what objects in this limit really is, but that's perhaps a little bit technical for what we're doing right now. Are there any other questions? All right, then in that case, I'll do the last thing and we can go have lunch or something. So Piotr talked about this Hahn, Raxid, Wilson, even filtration. And let me just write down again how it's defined. So it's the even filtration of it's given by some limit or R mapping to even rings of the double speed Whitehead filtration on S. So if you look at this quite a lot, it really looks like it's somehow global sections of a stack. And it turns out that so I had this functor. I have stacks and I have filtered stacks. There's a version of spectral stacks where you just look at even rings. And since even rings sit inside all rings, you get an adjunction. And here stack really means with this evenly faithfully flat topology of Hahn, Raxid, and Wilson. But it turns out that if you take the double speed Whitehead tower on something which is even, then it preserves evenly faithfully flat covers. So it produces flat covers in the sense of this result of shell that I erased now. So you actually get I don't know, by left-hand extending it along this, you get a functor which is colimit preserving in this way. If you ask, what is the composite, which I might call the associated even stack? Well, if I take cohomology of something affine, the even stack, and now I mean really this filtered cohomology, and I look at like with value with coefficients in the structure sheet, then I really get the even filtration of R out. And I could tell you a little bit more explicitly what the category of quasi-coherent sheaves for this even stack is, but the point is that there is a colimit preserving functor on stacks who on affines gives you the even stack, so to say. And I think I'll stop here.
Question. For Maria.
Is this like even construction you sketch there? All like related to what Gregorich does in this newer pre.
So what Rock does is that he just goes around this adjunction.
Okay, yeah.
And then it's a computation that the descent spectral sequence is the even filtration.
Yeah, but yeah. I mean,
But also, if I just, am
and go there and then take the inverting tau thing.
Yeah.
Okay.
And let me perhaps just say that one of the reasons why this works a little bit better in my situation than Rock's is that Rock uses this like stronger flat topology of Lurie. Whereas if you just do this like pi star flat type thing and the weaker flat topology here, then you don't have to do all of these like even periodization instructions that Rock does.
Yes.
Otherwise, a lot of what Rock proves goes through the story.
So you like recover ML or from TNF and stuff like that.
I would think so, yeah. Well, I mean, yes, if you do like go back, yeah.
Yeah, I mean, little thing, I don't know.
Other question.
It's just more philosophical. Since you say that map is not an equivalence, it's only just lexemetric model. Is there a sense in which one is better than the other? Or like what are the comparative advantages?
I think it depends on what you need to do. So one of the like really strong properties of the classical definition of synthetic spectra is that it contains spectra as a subcategory, and that you get this like section of the inverting tau, which means this is essentially what Robert does to produce like EK structures on more spectrum types, things like this. I cannot do this. Do this. I mean, on the other hand, it's more closely related to like here, and I guess this has something to do with like this is more like a spectral sequence bundle over spectra. Like you get an atom spectral sequence and a spectrum, but the atom spectral sequence in synthetic spectra like doesn't have to be very closely related. Where here it's really forced to be a lot closer. Whether that's a bug or a feature, you decide.
Maybe a question regarding the tau construct, like taking a stick with x tau, and then we look at UCO of x tau. Does this also admit a description as like, okay, on X, I can make a pre-sheaf from sending an open to like Zyn of.
I haven't thought about that.
Yeah.
That would be cool.
Let's think Marius again. So a couple last things. First of all,